All right, this is number 4. This is the back page of the Limits Derivative FRQ worksheet. Number 4 here. This is coming from an old FRQ problem from College Board. All right, so let f be a function defined by f of x. We have piecewise function, 2x plus 1. We have a linear graph that's existing to the left of 2, and then we have a polynomial quadratic function, parabola that's existing to the right of 2. So for a, for what values of k will the function be continuous at x equals 2 and justify our answer? Okay, so what values will k be continuous? We know that these piecewise function will be continuous everywhere in its domain. This is a linear function, there's no break. There's the quadratic function, there's no break. However, at 2, we want to see, do these two branches, are they going to connect to the same y value? Okay, if they connect at the same y value, then we know that the graph is continuous. But what we want to do is we want to determine the k values so that these two piecewise functions will connect at the same y value at 2. So what we can do is we can set both equations equal to each other. 2x plus 1 equals 1/2 x squared plus k, and then solve for k. All right. So replace x with 2 because that's the x value where we want these two equations to share the same y value. Replace x with 2, so x gets replaced with 2. This x gets replaced with 2, and then the only variable left is k. So we can solve for k. 4 plus 1 is 5. 1/2 times 2 squared is 2. So 5 minus 2 is equal to 3, so k is equal to 3. So now let's replace k with 3, and let's just ensure and make sure that both these piecewise functions will approach the same y value when x is equal to 2. All right, so we'll find the one-side limits. The limit as x approaches 2 from the left side of 2 for 2x plus 1 will be 4 plus 1, which is 5. From the right side of 2, we have the second piecewise function, which we've updated with the k value that we found. So 1/2 x squared plus 3, and then replace 2 in for x. So 4 over 2 is 2, 2 plus 3 is 5. So we see that the one-side limit on either side of 2 approach the same y value. So therefore the function is shown to be continuous at 2 when k is equal to 3. Part B, using the value for k found in Part A, determine whether the function is differentiable. So the difference here between Part A and Part B, Part A is asking for continuity. So continuity is saying, do the two branches arrive at the same y value? Are they going to be connected? Differentiability is saying, are the two branches going to connect in a way so that both branches will approach the same slope on either side of 2, so that when it connects at 2, the graph will result in a smooth curve, and where a slope at that particular point can be known. Okay, so what we're going to do is we're going to find the derivative for both of these equations, and then evaluate the limit as x approaches 2 for these derivatives and see if both branches arrive at the same slope. All right, so let's find the derivative for the first piecewise. So 2x plus 1, the derivative becomes 2. The derivative for 1/2 x squared becomes 1/2 times 2x, which is just x, plus, and then k is the constant, so k is going to go to 0. So then here we have our derivative. 2 is equal to 2 when x is less than 2, and then the derivative is going to be x for x is greater than 2. All right, so now let's evaluate the limit as x approaches 2. From the left side of 2 for f prime, if I plug 2 into the derivative, that still remain 2. If I plug 2 into the second piecewise derivative, I'm going to also get 2. So we know that the one-side limit for the derivative is equal to 2. Therefore, function is differentiable. All right, part C, let k is equal to 4. Determine whether the function is differentiable at x equals 2. So let's update let's rewrite our piecewise function. 2x plus 1 for x is less than or equal to 2, nothing changes there, but here 1/2 x squared, and then k, we want to replace the k with 4. All right, before we can even determine whether the function is going to be differentiable or not, let's first determine, is the function even going to be continuous? Okay, even going to be continuous. So to determine that, we're going to evaluate the limit as x approaches 2 from the left side of 2, and then evaluate the limit as x approaches 2 from the right side of 2 to see if they even are connected at the same y value. So to evaluate the limit as x approaches 2 from the left side of 2, we get 2 times 2 is 4, 4 plus 1 is 5. On the right side, if I plug in from the 2 from the right side of 2, 1 half x squared plus 4. If I plug 2 in for x, I get 4. 4 divided by 2 is 2. 2 plus 4 is 6. So we see that the limit doesn't even exist. Hey, 2x plus 1 is going to arrive at y value of 5. Limit as x approaches 2 from the right side of 2. This branch will approach y value of 6. So that means that these two graphs have a non-removable discontinuity. The graph is not going to be connected. So the graph is not even continuous. So we've shown that because limit doesn't exist, the graph isn't continuous. So the graph is not continuous, then there's no way our graph can be differentiable at x equals 2 either.